All right, welcome to lecture 22. So this lecture is mostly about the mean value theorem and related results about derivatives. So on our way to the mean value theorem, the first little thing we're going to prove is that the familiar fact, right? That if a function achieves a maximum at a certain point, and it happens to be differentiable there, then the derivative should be zero, right? So of course it's possible that so if a function achieves an extremum at a point, and if it is differentiable there, then the derivative is zero, okay? At the point, of course. So, it's possible that it might not be differentiable at an extremum. Like, for example, f of x equals absolute value of x achieves a minimum at x equals 0, but is not differentiable there. So the statement doesn't apply. Right. But something like f of x equals x squared also achieves a minimum at x equals 0, and it is differentiable there. And of course, it's easy to calculate the derivative at x equals 0, but this fact also tells us that f prime of 0 is 0. So, it's, like I said, it's a familiar idea. Kind of the intuitive picture here, and this really is the basis of the argument too, is that so for small enough delta, let's say, for a small enough delta, if f prime of a is less than 0 or f prime of a is greater than 0, we have the following pictures. So, when f prime of a is less than 0, then, so let's say this is a, right? And let's say this is a minus delta, and this is a plus delta, some suitably chosen delta, right? Then, roughly speaking, f looks approximately like a straight line, quote unquote, approximately. So approximation of f, right? And similarly, if f prime of a is greater than 0, then we would have a picture like this, where the function is increasing, and this is also the approximation here, right? So clearly here f of x is greater than f of a, and here f of x is less than f of a, and similarly here f of x is less than f of a, and here f of x is greater than f of a. So in neither case can f of a be either possible extremum, because you can find points on either side where the value is either bigger or smaller. So, sorry, this is supposed to be f. So, yeah, you've probably seen this idea before, but just to remind you that this is the basic idea, and this actually is the basis of the argument we make as well. So, here's the proof. This was theorem 29.1, by the way. So this is theorem 29.1. Suppose for, contradiction, I guess. Although this is really more of an argument by contrapositive, but that f achieves a maximum at x naught in the open interval AB, and f prime of x naught is greater than 0. Then, right. So, yeah. Sorry, one sec. So this we're assuming without loss of generality. It's basically identical. The argument is essentially identical whether or not you're considering a maximum or a minimum, because in either, really, no matter what, in either case, whether the derivative is positive or negative, we're going to end up being able to construct points which are both greater, where the value of f is both greater and less than f of x naught. So yeah, but whatever. Anyway, yeah, so this maximum thing is just one of these simplifying assumptions. So this means, by definition, that the limit as x approaches x naught of f of x minus f of x naught over x minus x naught is greater than 0, right? So what this means is that, so this equals some number, right? This limit equals some number greater than 0. So for example, by picking epsilon, right? If you remember the epsilon delta version of the limit, of the two-sided limit, so using the epsilon delta formulation of two-sided limits, we can find a delta greater than 0 such that for all x in x naught minus delta, x naught plus delta, we have that f of x minus f of x naught over x minus x naught is greater than 0. And if you want to think about it this way, like whatever the value of f prime of x naught is, say we set epsilon equal to, so consider taking epsilon equals f prime of x naught over 2, right? If we take epsilon equals f prime of x naught over 2 and then choose delta so that, this is within epsilon of f prime of x naught, that forces it to be positive, right? Because that means that it's stuck between, it's basically, if it's within f prime of x naught over 2 away from f prime of x naught, then the value of this actually has to be between f prime of x naught minus f prime of x naught over 2 and f prime of x naught plus f prime of x naught over 2. But the lower bound on that is f prime of x naught minus f prime of x naught over 2, which is just f prime of x naught over 2. So this is stuck being positive for that value of delta, right? This is like a common theme, that when you have a quantity, some function or a sequence or whatever that converges to like a positive number or a negative number or something, you can, by controlling the limiting process, you can force that quantity to stay either positive or negative or whatever. So yeah. Okay, so then, but for x not less than x less than x naught plus delta, this means that f of x minus f of x naught is greater than 0, because since x minus x naught is greater than 0, right? So we're saying that this quantity, this ratio here is positive, right? So that means that if the denominator is positive, then the numerator also has to be positive, right? So we chose this delta so that for all x in this like symmetric interval, for all x in this symmetric interval, this quantity is positive. So in particular, for values of x in the right half of the interval, so when x happens to be bigger than x naught, then the denominator is positive, so the numerator also has to be positive. But then f of x is greater than f of x naught for these values of x, contradicting the assumption that f achieved its maximum at x naught. So the proof for right. So the proof for f prime of x naught less than 0 is similar. So you take delta for x in x naught minus delta, x naught plus delta. We have f of x minus f of x naught over x minus x naught less than 0, right? And then when x happens to be less than x naught, the denominator is negative, so the numerator has to be positive. Or sorry, yeah, when x is oh yeah, no. In this case, when x is greater than x naught again, right? When x is greater than x naught, then the denominator is positive, so the numerator has to be negative. So that would mean you'd have a value of f of x, which is oh no, because we're still assuming that it's a maximum, right? So yeah, just look to the left then. Look to the left. So then this is the denominator is negative, so then the numerator would have to be positive. So that would mean you'd have other values of f that are bigger than f of x naught, contradicting. So then when x naught minus delta is less than x naught, we have f of x is greater than f of x naught again, right? So yeah, anyway, well, yeah, like I said, it's similar. I don't know why I belabored that so much. Anyway, so just to comment about, you know, local extrema. So like as a corollary, if x naught is a point such that there exists an interval, you know, CD containing x naught and such that f of x naught is greater than or equal to f of x for x in CD, or f of x naught is less than or equal to f of x for x in CD. So this this condition that I just wrote here this is how you define a local extremum. So, so i.e. x naught is a local max or min. Oops. Then this theorem still tells us, right? We actually, in the theorem, we were really only talking about global maxima and minima, but by passing to the restriction, right, this tells us that f prime of x naught equals 0 for these points 2, because we can apply the theorem to f restricted to the interval CD. So if you apply the theorem to the restriction, right, once you pass through the restriction of f to this interval, then x naught becomes a global max or min, right? I mean, it started off as a local max or min, but once you restrict to this small interval, then for the restriction, it is actually a global max or min because there are no other, extrema in that interval. So then if you look at the derivative of the restriction, that has to be 0, right? I mean, if f, so, right. Also, we're assuming, and f is differentiable at x naught, right? We're of course assuming that f is differentiable there. So if f is differentiable there, then so is the restriction, right? And the value of the derivative of the restriction is the same as the value of the derivative of f. It's all very trivial to prove these things. So the theorem tells us that the derivative of the restriction, so f restricted to CD prime at x naught equals 0, that tells us that f prime of x naught equals 0 as well, right? Because they're the same. Yeah, I mean, if the restriction is differentiable at a point, then f is differentiable at the same point, and they have the same value, and vice versa. If f is differentiable at a point, then the restriction is differentiable there as long as the point is in the interior of the set to which you're restricting. So in this case, since it's an open interval, that's automatic. Anyway, so yeah, you can deal with local maxima and minima using this theorem as well, even though it's only phrased in terms of global max or min. Yeah, so that's all for this video. See you in the next one.